All right, welcome back, everyone. It's November 12th. I just posted the third exam, so let me know if you didn't see your exam in Canvas. It should be there, the graded exam. Um, so we're just looking at the calendar here. We're going to finish up Chapter 5 this week, and then Exam 4 will open next week, right? So that'll open on Monday. And so we're pretty much right on track. We might take a few minutes, maybe like 30 minutes on Thursday to finish up chapter 5, but yeah, well, we should have some time to review there on Thursday. And then just like normal, just like for the last exams, if you'd like, you can watch this review recording that I've made earlier. Okay, so you can see that. I think it's about an hour. And then if you look in there, we have those practice problems again. So just do those practice problems, watch the video, come to class on Thursday, do your homework uh, to get prepared for that exam. That'll cover chapter 5, just chapter 5. And then after that, it's just a couple of weeks until the end of the semester. So after exam 4, we'll do chapter 6. Chapter 6 doesn't have its own midterm, but it will be covered on the final. So that final, that'll be open that second week of December there, and it'll be comprehensive. It'll cover chapters 1 through 6. So chapter 6 will be tested on the final. Okay, do you guys have any questions you want to go over before we jump back into chapter 5 and try to knock out as much of this as we can? Anything you want to go over from the homework? Any lingering questions? Okay, so where were we? We were in probability. Okay, so pretty much every intro stats class will have some kind of section on probability. Some do more, some will use like a couple of chapters, some do a little bit less. Uh, we kind of pared it down a little bit here, so it's just a few sections of chapter 5, but it does provide a really useful foundation for stats. Um, so I think we almost finished this problem here. We were looking at the relationship between sectors of the economy, sectors of the transportation economy, right? So these are all transportation workers, and we were looking at the relationship between the amount of sleep they're getting and various sectors, right? So, who knows? Maybe one of these sectors is famous for having poor working conditions, right, or something like that, and we're trying to trying to see if that really works, if that is true for sleep, right? So so it's a contingency table, and we were using it to practice with these rules of probability. So I think we got to see it. I don't remember if we finished it or not. So let's just do C again, and then maybe we'll also look at this box of marbles in the next example. So it says, what's the probability that two randomly selected transportation workers are both train operators if the selection is done without replacement? Okay, so we know that without replacement is a synonym for dependence, right? So we have a dependent situation here, and we have the multiplication rule, right? Because if both are train workers or train operators, then the first one will be a train operator and the second. So we know that we can break that up with multiplication, right? So it's going to be the probability the first is a train operator times the probability the second is a train operator. But but if the first is a train operator, the first one that we select is a train operator, that's going to change the probability that the second one is also a train operator. So we have to be careful with that second part there, right? So the probability the first one is a train operator. Well, how many train operators do we have? There's 180 train operators, right? So there's 180 ways of choosing one out of the 795 in the study. So then we multiply that by the second probability here. Well, if we're going to reach back in and randomly select somebody, or use like a random number generator, right, to do that, there's no longer 180 people in there. There are 179 train operators. And there's also not 795 people anymore, there's 794. So we see this pattern very, very frequently in probability theory, where we have this descending kind of pattern. So very common to see that. So then we just pull out the calculator and work through it. So 180 divided by 795 times 179 divided by 794. Okay, and we get about a 5% chance. And that makes sense. If you randomly select two people out of here, the train operators, it's not the largest group. In fact, it's the smallest group in there. So it wouldn't be very likely to get two train operators in a small sample of two. It wouldn't be unusual, but it's pretty close to unusual. Remember, unusual being less than a 5% chance of happening. So this is a little bit more than 5%, but it's kind of borderline unusual. Okay. All right, so you guys try one more of these. I don't think we did this one last time, but so on your fourth exam, you will have at least one of these contingency tables, and you'll use it to calculate probabilities. So stuff just like this. Then you'll probably also have another probability problem that resembles this kind of scenario where you've got like a box or a bag of either marbles or maybe chips with numbers on them, or tulip bulbs with different colors. These kinds of problems are kind of easier to set up, and they're really good at testing students' knowledge of the probability rules. So you'll probably see one of these on there as well. So here's the scenario, and I think we've seen something kind of like this before. We have marbles in the bag. 6 of them are blue, 5 are red, and 2 are green. We're going to randomly select 2 marbles, and we're going to do this without replacement. Okay, so you're going to reach in, you're going to pull out a marble without looking, and you note the color of the marble. Then you're going to put that marble aside and reach back into the box and grab a second marble. Okay, because you're not replacing the first one, it does change the probability of the second one. Now, it's probably not going to be, it's not always like a, like a really noticeable difference, but like this one, it's not super night and day kind of difference, right? It's subtle, but it's important to get it right. So just like this one over here, we're gonna have a slight difference because we're doing this without replacement. Okay, so you guys do 3 of these. What's the probability they're both blue? Then what's the probability the first is blue and the second is green? And then what's the probability the first is green and the second is blue? So I want you guys to try these 3, and then we'll move into 5.6, which is our last section of pure probability. Okay, so I'll just go quiet for a minute or two and let you guys practice with these. Okay, does anybody have the probability they're both blue for us? I'm just going to start it here. If they're both blue, that means the first is blue and the second is blue. And the reason I wrote it like that is because I know that and goes with the multiplication rule. So it's going to be the probability that the first is blue times the probability the second is blue. So the first one is pretty straightforward, right? We just count the number of blue, right? So there's so there's 6 plus 5 is 11, plus 2 is 13, right? So there's 13 marbles to choose from, and there's 6 of them that can give us a blue. Then we multiply that by the probability the second one is blue. But because it's dependent here, that second probability is a little bit different, right? There's no longer 13 marbles to choose from. There's only 12, and there's no longer six blue ones to choose from. There are 5. So we see that descending pattern that's very commonly associated with a dependent kind of situation. Whoops. Sorry about that. Oh, what am I doing here? Keep pressing the wrong thing. There. Okay, so we go 6 divided by 13 times 5 divided by 12, and it's about 19% chance. Okay, so 0.192. So about 19% chance that you randomly select 2 marbles, they're going to be blue. And this really is how the world works. If we sat around with a box that had this, number of marbles with these colors, and we empirically, just tested this out, eventually we would get something converging to 19.2 using the law of large numbers. Okay, so can anybody give us B then? What's the probability the first is blue and the second is green? I would love for somebody to give us this one. Great. You're exactly right, Shoshana. Perfect. It's about a 7 or 8% chance of occurring. So again, I like to write it out with the and because that tells me it's multiplication, right? Now, it's a dependent situation, so that second probability will be altered. But the first one is the same. It's 6 out of 13 blues. And then green, there are 2 green out of 12 marbles, right? So we multiply those together, and yeah, we get 0.0769. Okay, and then C, I like to throw that one in because it kind of seems like it should be the same. So your intuition, tells you, yeah, maybe it's the same, but maybe it's different, right? Maybe the order somehow changes it. And we don't have to guess and use intuition here. We can use our formula, okay, to find the answer. So the probability that the first one is green is 2 out of 13. And then the probability that the second is blue is 6 out of 12, right? And so we see it's the same. It should be the same number. With multiplication, order doesn't really matter, so we can swap those two numerators, and we end up with the same probability. So if you were thinking just intuitively that it should be the same, well, you were correct. Sometimes intuition really does work well with probability. Sometimes it goes really badly, and sometimes intuition is really far off the mark. But here, it I think it does line up with what the formulas tell us. Okay, so it's good to have both. It's good to have an intuition, but it's also nice to have formulas for more difficult situations. So that's most of our probability rules. Let's go back to our formula sheet here and recap. So when we're looking at a compound event where it's an or, A or B, then we use the addition rule, right? So sometimes in life it's A or B, right? You apply for a job and they say, okay, you need 3 years of experience or a degree, right? So that happens. And so when it's an or, it's addition. And if they're overlapping, if they're not disjoint, then you have to subtract off the overlap, okay? If it's an and situation, and those happen too, right? You apply for a job and they say 3 years of experience and a degree, right? That's more exclusive, right? The or is inclusive, right? The and is more exclusive, right? 2 or more things have to happen simultaneously or in a row, right? So with ands, it goes to multiplication. Now, if you have independent events, it's quite simple. If it's just a simple multiplication. But if you have dependent events, then you have that case where you have to update the second probability. Okay, so we also talked about the complement rule. That's useful sometimes. So that's like rain and not rain, right? Okay, so we've discussed those. The last thing we need in our pure probability section is expected value of a random variable. Okay, so what does expected value sound like? It sounds like a mean, right? So we're going to have a random variable, which we'll define in a second, and then we want to find the expected value of that random variable. Okay, so this will conclude our pure probability stuff, and then we'll get back into stats. So we need to talk about a random variable first before we can understand the expected value of it. So what's a random variable? Well, it's simply a random process with a quantitative outcome. Okay, so it could be something like rolling a die. When you roll a die, you do have a general idea of what's going to happen, right? You know it's going to be some number between 1 and 6, but there is an element of randomness. You don't know if you're going to get a 2 or a 5, right? And it also has a numeric outcome, a quantitative outcome, right? You get a 1, a 2, 3, or all the way up to 6. If you roll 2 dice and you count the number, count the numbers, you add the numbers in, of the 2 dice, that's also a random process, right? In this case, you can get something between 2 and 12, right? So there's randomness there. So that's basically what a random process is. Now, these random processes have what's called a probability distribution. And with the probability distribution, it's basically a table where we look at all of the possible outcomes. Okay, so typically we'll have it in a table, a vertical table, and one of the columns will have all of the outcomes of the random process. Then the other column of the table will have the probability associated with each of those outcomes. Okay, so enough talking. Let's jump in to a problem and actually practice with this. Okay, so back to gambling. And I think I've mentioned a few times the kind of historical connection probability has with gambling. So we'll do a couple more gambling examples, and then we'll go into other things that are related to the expected value. So in roulette, so if you've ever played roulette, this is a game of chance where you have let me see if I can find a picture of it for you guys online here. So let's look up roulette wheel simulator here. You've probably seen one of these before. Even if you don't play roulette, you might have seen it like on like a movie or something. So let me see if no, that didn't work. I'm going to give up here real quick if this doesn't work. But basically, there's a wheel, and on the wheel are these slots. Each slot has a number, and then when you play, you put some money down on the table, or chips or something, right? And then you predict what number it's going to be, right? So maybe we'll go for 17. Okay, so I'll go for a 17, and let's see, or maybe I think this is how you play. I've never actually played before, but so maybe we'll bet on 17, and then the person at the table will spin the wheel, right? And then there's this ball that spins around, and eventually it loses energy and it falls down into one of the slots, right? So you can see that it landed on 7. It did not land on my 17 over here, right? So I would lose that one, right? Okay, so so if you gamble, if you go to casinos, you've probably seen this, or you might have seen it on a movie. So we're going to use the idea of the expected value to see, what kind of odds there are, what we can expect to happen when we play roulette. Okay, so so our random variable will be the money won or lost in a single roll of roulette. That should be a random variable because we don't know what's going to happen when we sit down and play this. We might win, we might lose. Okay, so there's an element of randomness to it. So the next step is to find the probability distribution. So the probability distribution it typically has a couple of columns like this, and we have a list of all of the values of the random variable. So the way this one works is you put $5 down on the table, okay? And let's say we bet on the number 17, okay? So we put $5 down. If the ball lands on 17, then we win $180 and we take our $5 back. Okay, so the $5 sits there on the table. If you win, you take your 5 back and they give you $180. Okay. But if you lose, they take your 5 and then you're done, unless you want to play again. Okay. So, the two events are you win or you lose, right? So if you win $180, right? Because you get your $5 back. So the $5 it just sort of floats and then you get it back, and so it's not like you won 5 or lost a 5 or anything like that, right? The 5 is just sort of irrelevant there. You win $180, okay? If you lose, then you really do lose the $5. Okay, so it's negative because that's money going out. The 180 is positive because that's money coming in, right? So those are the two values of the random variable. Those are the only two things that can happen when you play this game, typically. Then we have another column where we list the probabilities. Well, if you look on the roulette table here, there are 38 different slots for where the ball can fall, right? At least as I understand it. Yep. So there's 38 there, or there should be. And so that you have a 1 in 38 chance of winning, right, when you play. So doesn't sound like great odds. So the winning, it's 1 out of 38. And so let's go ahead and turn that into a fraction, into a decimal. So we go 1 divided by 38. Okay, so it's not super likely that you win when you play roulette once. Okay, so that's going to be 0.02632. So first of all, I forgot to ask, why don't we play roulette all the time? If you can win 180 or lose 5, why don't we just play roulette all day long? Because 180 is more than 5, right? Well, it's because of the probabilities. The probability of winning is so much smaller than losing. In fact, the probability of losing is 37 out of 38, right? Because there's 37 ways of losing when you play roulette once, right? So we divide by the 38, and each time you play, there's like a 97% chance you're going to lose your money, right? So it doesn't sound like very good, very good odds to me there. So, so what the probabilities do are they weight the values of the random variable. So basically, what we're going to calculate now is a weighted average. So you've probably heard of a weighted average before. So let's go back to our formula card here. So with the expected value, we have our values of the random variable. Those are x, and then we have the probability of each of those values of x. So the next thing we're going to do is we're going to use the probabilities as weights. So each probability is going to multiply its corresponding value for the random variable. So how does that work? Well, I usually draw out a third table, a third column for my table. Okay, so we'll have x times p of x. Okay, and so we just multiply across. Okay, so this is the number I have here. I'm going to go ahead and multiply that by -5. Okay, so -4.8684. And then here I'm going to go 180 times 0.02632. So I go 180 times 0.02632. And we see that that small probability took the 180 winnings, right, and it shrank it down to a much smaller number, right? It's now down to 4.7376. So it really, it shrinks the number down a lot, okay? So then, what's the next step? So we have our column of these quantities. Then if you remember the capital sigma, that means we're adding, right? Okay, so we've seen sigma before, right? This capital sigma, we did that back with our mean, we did that with the standard deviation, and we use it again here with the expected value. If you open up a book on probability, you'll see sigma on almost every page. It's just, it's ubiquitous, okay? So, so we add those numbers. Okay, so I'm going to go plus 4.8684 minus, and there we go. It's about 13.13. Okay, so since we're dealing with dollars and cents, doesn't hurt, I think it makes sense here. It does make sense to go ahead and round that to 13 cents. Now it's negative, and the negative is important. If you're the player, you don't want to see that negative there, right? That means it's the odds are against you, basically, right? If you play this game enough, the law of large numbers is going to come in and guarantee that you lose, okay, your money, right? Maybe not on this game, or maybe not on this roll or that roll, but in the long run, and who knows how long that is, maybe over 30 games, maybe you have to play 300 games, but eventually you're going to start, you know, you're going to be in the red, right? You're going to have lost money here. Okay, so the expected value is negative 13. Now, how do you lose 13 cents at roulette? Well, you can't, right? Right? Either you win 180 or you lose 5. So how do you lose 13? Well, this is the long run kind of law of large numbers kind of interpretation here. We're not talking about any one game. We're talking about the average for many, many games. So in other words, if you sit down, if you bring a stack of money to the casino and you start playing roulette, what's going to happen? Usually you're going to lose, right? You're going to lose, you're going to lose, you're going to lose. But every now and then you're going to win, right? And then you'll lose, you'll lose, you'll lose, you'll lose, you'll lose, 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 lose. Eventually you win again, right? And then so if you keep playing, and then at the end of the session, you add up all of your losses and your winnings, you divide by the total number of games you play, it's going to average out to be about 13 cents. Okay. You might remember that example we did at the beginning of the chapter where we flipped coins and we saw that the graph converged to the true probability. So that's kind of what would happen here. Our losses would converge to, on average, 13 cents per game. So you don't want to play roulette as a strategy for making money. It might be fun, and it might be worth it because of the entertainment you get out of it, but it's not going to make you wealthy to play roulette. Okay, so if you played 1,000 times, how much would you expect to win or lose? Well, let's see. So 1,000 times negative 0.13, you're looking at about $130 in losses, right? So, that's a lot of roulette games and just $130 in losses. So, if you're looking to be entertained, that might not be a bad deal. Okay, good. So there we go. Any questions there about the expected value? And this truly is how casinos decide how to, set up the rules of their game, right? They can make you pay $5, or they could have done this at $3 or $10, right? So they can alter that. Then they can also alter the winnings, right? They can make it $200. They can make it $50, right? And so when they set these games up, where did the 37 and 38 come from? Sarai's got a question here. The 37 and the 38 come from the fact that there are 38 numbers on the roulette wheel. So if we go back to the roulette wheel here, there should be 38 on here. And notice that 0 is a number, so it might only go up to like 37, but does that make sense? There should be 37 slots on your typical roulette wheel. Okay? Does that answer your question, Sarai? So if there's 38 slots, then there's 38's the denominator, right? Because there's 38 ways that the ball can land. And then for losing, there are 37 slots that will lose, right? There's only one that's 17, so 37 ways of losing. All right. Forget what I was saying. So yeah, we have our negative 130 expected value. Okay, good. Oh, okay. Yeah. So this really is how casinos and these like online gambling websites set up their games, right? They know how much they're going to pay out. They know how much it's going to cost. They know the probability of winning or losing, and then they set up this equation, and it tells them, hey, is this game going to be a winner for us or a loser, right? So good. Any questions there? Let's do another one about a topic totally unrelated to gambling, or at least seems like it would be unrelated to gambling. Let's look at realty. Okay, let's look at real estate for a second. So here we have this real estate office, and so the real estate office, they'll have these data sets where they look at how many homes were sold, just typical information they would record, and we're going to think about the mean or average number of homes sold. Okay, so if you're a real estate agent, sometimes you'll have a good month and you might sell like 2 or 3 homes, right? And apparently some have a really great month and they might sell 6, which is a lot. But it's also quite common to just have that month where there's no business at all, right? So it kind of goes up and down a little bit. But they're not all equally likely. Okay, selling 0 homes is not as likely as selling 6 homes. And so, but there's some randomness to it, right? As a real estate agent, that you're probably going to sell, maybe 1 or 2 homes, or maybe 0 homes. You're not going to sell like 20 homes, right? Usually. So there's an idea of what it's going to be, but it is somewhat random, right? It's not for sure at the beginning of the month how many you're going to sell. So it is a random variable, and it is numeric. And then so that's the first column of our probability distribution. Then the next column is the probability of each level of the random variable. So it turns out that selling 0 homes is the most common uh, event. Okay, so it's the most likely. It has a 24% chance of happening. Selling 5 homes apparently was very unusual. Okay, only about 1% of the time did that happen. So they're not equally likely events. So if I want to get the mean or the average here, we're going to use that that formula for the expected value. So it's right here. And so again, it'll be on the formula card, so you'll just bring this with you to the exam, right? So that formula calls for the product of each value of the random variable by its associated probability. So I always set it up with a third column here. I go x times p of x and we just multiply across. Okay, so I'll do the first couple of easy ones for you. So 0 times 0.240, 1 times 0.13 is 0.13, 2 times 0.16 is 0.32. So you guys practice with this. See if you can fill out the rest of that third column there on our probability distribution. And then what we'll do is we'll kind of get an idea of what the average number of homes sold for a month is for this particular office. Okay, so just multiplying across there, that's going to be 0.63, right? Can anybody give me these numbers? Anybody get the next few here? 4 times 4. Great. Thank you, guys. Yep, 0.05 and 0.66. Perfect. Thanks, everybody. All right, so So what are those? Those are the kind of the weighted values for the various levels of the random variable. Okay, so the last step, if you look at the formula, is to add those up. Okay, so we're just going to add vertically down that last column, and I believe we get 2.35. Okay, so what does that mean? Well, on average, your kind of typical number of homes sold for a realtor at this office is about 2.35 homes. Now, you can't sell 2.35 homes in a month, right? You can sell two, you can sell three, you can sell zero. You can't sell 2.35. What does that mean? Well, it means, okay, look at kind of the long run average for their realtors. It's about 2.35 per month, right? So it's averaged over a larger data set, right? Okay, so you guys try one. Okay, we're going to return to the world of gambling here. Unless you only sell the kitchen. That's right. Yeah, it um yeah, it's quite a interesting market, the real estate market. But yeah, let's switch over to life insurance here, which is basically it's kind of like another kind of gambling, right? Maybe it's a little bit more admirable than roulette, but basically when you buy life insurance, right? Um, it's a gamble. You don't really know if you're going to need it for that year, right? So if it's a 1 year term life insurance, basically you buy it for 12 months, and if you die during that time, then your beneficiary receives the money, right? And so what if you don't die during that year? Well, they just keep the 200, right? The amount that the policy cost. So it's a bit of a gamble, and so it works very similar to the roulette situation. So with this policy, we're gonna we're gonna have a $250,000 life insurance policy, and so it costs $200. So how does it work? So if this person dies during the year, their beneficiary gets $250,000, and they pay $200 for this. So so how do life insurance companies work out how much to charge for these sorts of things, right? Do they charge 200? Do they charge 500? Do they charge 50? You know, should they have a $250,000 policy? Should they have a $100,000 policy? Well, it depends mostly on how likely it is the person will need it. And I know it's kind of somber, to talk about it, but it's basically how likely it is that this person will die during the course of the 12 months, right? So there are people who do this for a living. They're called actuaries, okay? And it's a very well paid profession. They're basically like statisticians, and they have these huge data sets, and they try to figure out how likely it is that somebody will die, or if it's car insurance, have a car accident, or if it's home insurance, how likely it is that the home will burn down, stuff like that. Okay, so they have these huge data sets, and they're using the law of large numbers to find these probabilities. So for a 20-year-old female, it's going to cost less than a 65-year-old male, right? Because 20-year-old females have a much less much smaller chance of dying, and so it's actually quite likely that a 20-year-old female will survive for another 12 months. If we look at that probability, it's more than 99.9% chance, right? So that's good. So what I want you to do here is compute the expected value of this policy, and we'll do this from the perspective of the insurance company. Okay, so we need a probability distribution, and so what we'll do is we'll list the possible outcomes. Okay, so the two outcomes are the person lives for that whole year and doesn't need the policy, and the second possible outcome is that they die. Okay. So each outcome will have an associated numeric value for the company, right? If the person lives, then the company keeps the $200, and then, if they want to buy another policy for the next year, they can do that. But for that 1 year, it's done. Okay, now if the person dies, then they keep the 200, but then they have to pay out $250,000. Okay, so um, so it's 249,800, but it's a negative number, right? The negative sign is very important. If you drop that negative, and sometimes it's kind of uh, tempting to do that, you really do mess up the whole problem because this is money going out, right? And so it changes the expected value of the policy. So that we could call X. Then each of these events will have an associated probability. So the probability that the person lives is 0.999544. And we're not making that number up. There's actually, you can look this up. It's called the National Vital Statistics Report. And there's a whole table of these numbers for various, gender, age combinations. And there's probably, there's other variables they'll look into. So if you apply for life insurance, they'll make you go in and get medical testing done, and they look at your age and where you live, zip codes, probably stuff like that. Anyway, so these actuaries have these tables, and they really do calculate these numbers. Okay, so now what's the probability of dying? Well, living and dying, these are complementary events. So the probability of dying is going to be 1 minus the probability of living. Okay, so um, so since the probability of living is so high, the probability of dying for a 20-year-old female in the next 12 months is very small. So um, there we go. So what is that? Maybe 4 in 10,000 end up dying in 12 months. So that's pretty good news. Then to get the expected value, we'll follow the same formula. We create a third column, x times p of x, and then we add those quantities. And that's what I want you to do. Okay, so I've set up the distribution here for you, and I want you to find the expected value. And by the way, I love putting the life insurance policy problem on the fourth midterm. Very likely you'll see this. Well, I can guarantee you that you will see an expected value problem on the fourth midterm, and it's most likely going to be this life insurance problem because I find insurance to be such an interesting topic. Um, it's basically how we spread risk out in society. So give it a try. I'll go quiet for about 4 minutes here, and at 12:16 we'll come back together and talk about the expected value of this policy. Okay, so let's see, we have just multiplying across there. And how many decimal places should we use? Well, write down as many as you can stand to write out, because if you round too quickly in these problems, you can really start messing things up. Um, so did anybody get the final answer when we add those up? What is the expected value? 86. Great. Thank you, Lana. That is exactly correct. Great. So it's positive 86. And so that means this will work for the company, right? So these numbers here mean that the policy, if they sell enough of them, if the law for the law of large numbers to kick in, as long as they sell enough of these, then they will make money on this policy. Okay, so they can move forward with this policy. Now, so I think you can tell very quickly that it all comes down to how accurate these probabilities are. Okay, if they don't have an accurate read on how likely it is somebody's going to survive, then if they start selling these policies, they might lose a lot of money on it, right? So it's really important that they can have a way of accurately calculating these probabilities, these likelihoods. Okay, so that's why actuaries make a lot of money, because they can actually figure out how likely these products are to work or not. So $86, what does that mean? It doesn't mean they're going to make $86 on each policy, right? In fact, that never happens. They either make 200 or they lose about $250,000. So what's going on here is a law of large numbers kind of situation. So if they sell a bunch of these policies, usually they're going to be making 200, right? So they make 200, they make 200, they make 200, make 200, and then every now and then they pay out like 249,800, right? So if you add up all of the money in, money out, you divide by the total number of policies, it's gonna converge to about $86, okay, per policy. So good. All right, so I hope you find that interesting. Let's move on though. This is a course in stats, not probability. We do need the language of stats and we do need the language of probability, but we do want to spend most of our time talking about stats. Okay, so any questions there about the expected value or just probability in general? That's pretty much it for pure probability. Let's get back into sampling. Okay, and so in chapter 5, what have we done so far? We've looked at understanding associations between variables, right? Then we looked at probability theory, and now we're going to return to looking at relationships between two variables. Okay, so earlier we looked at contingency tables and segmented bar plots, conditional distributions. Okay, now we're going to come back to inference. Okay, so we're going to basically build confidence intervals and do hypothesis testing for the case where we have two categorical variables. Okay, and so what it works out to be is a difference between two proportions. Okay, so rather than me read this off to you to begin, I think it's just easier if we jump into a problem to help us kind of understand what's going on here, and then we'll come back and more carefully discuss all of that, all of the details, right? So let's just jump in and try one of these. So on this one, we're looking at BMI, okay, so that's body mass index, and so according to this, it says that a BMI between 20 and 25 indicates a normal weight, okay? And then so that would be categorical, right? So using this definition, somebody is either of normal weight or they're not, right? So that's a categorical variable, right? And so there is some, some proportion of people of normal weight, right? So we could have studied this back in chapter 3. The difference here is that we have another categorical variable, and this one is gender, okay? And so very common, if you're doing like health studies to see if there's some kind of gender effect, is some condition, is it more common among males and females or vice versa, right? Or is it the same for the two, for males and females? So that's the second categorical variable here. Okay, so how did they look to see if there's a gender effect? Well, they take a sample of males and they take a sample of females, right? So the picture we want to have is population of females, right? And some proportion of those females, this is all females, some proportion will have that normal weight, right? And then we take then we look at the population of males, right? And so this is all males. Some proportion of all males will have a normal weight, right? Between 20 and 25. And so the idea is we're trying to see if there's a difference between these two proportions, right? PF and PM. But nobody knows what PF or PM are, right? Because nobody has a data set that has everybody's BMI in it, right? So the best we can do is sample, right? So we take a sample, right? We get this female, this one, right? We get a nice representative sample, okay? And then we calculate the proportion of those that are of normal weight, right? And we call that the sample proportion. So we put a hat on it to distinguish it from PF, right? So it's PF and PF hat. Then we do the same for the males, right? We get this one, we get this guy, and we have a sample of males, and then some proportion of them are of normal weight. That's PM hat, right? So what are those numbers? Well, 203 out of the 750 males were of normal weight. So if we divide 203 by 750, we get 0.271. So in that sample, about 27% of males were in that category. What about for the females? So for the females, we take the 270 and divide by 750, and it does give us a higher proportion. About 36% of the females in the sample were in that category. So you guys see the two categorical variables? Okay, so the first one is normal weight versus not normal weight, right? So that's categorical. And the second one is this gender, males and females. Okay, now we'd really like to know this right here. What is that difference? But we kind of have to give up, right? Because nobody knows what everybody's BMI is. So the next best thing is to take our sample proportions and subtract those. So I'm going to take PF hat minus PM hat, and that will give us what we call our point estimate for the difference between the proportion of females of normal weight and the proportion of males of normal weight. So that works out to be 0.089. Okay, so is there a difference between the proportion of all females in that group and the proportion of all males in the normal weight group? Well, the point estimate is about a 9% difference. So among our two samples, it does appear that the females have a higher percentage of people of normal weight. It's about 9% higher among the females in the sample than among the males in the sample. But you know how it is with sampling. There's always going to be some sampling error, right? And maybe if we did this again, if we took another sample, maybe the sample proportion of females would be lower and maybe the sample proportion of males would be higher. It's very possible. And if that were to happen, then the point estimate would be smaller. Or maybe it might even flip and it might go negative. Maybe a higher proportion of males are of normal weight than females, right? We just don't know yet. So how would we know? Well, we would need a distribution, right? And so it turns out that we can use the normal distribution here. Okay, why is that? Well, if you study mathematical statistics theory, it says, okay, if you have a variable that's normally distributed, like say PF hat, right? In chapter 3, we talked about why that would be normally distributed. Okay, so if you have a normally distributed variable and you subtract another normally distributed variable, so I mean, we can't prove it in this class, but it is true that a difference between two normally distributed variables is also normally distributed. So we're actually back to the normal distribution. We're back to the z distribution, which is great. We're very comfortable with the z distribution. We've been working with it for a couple of months now. So it should be pretty easy for us. Okay, so turns out that we can use the normal distribution. And so at this point, I'm going to do this problem quickly using software, so you can just kind of get a big picture idea of what's going on. Then we'll go back through the details of the inference here. Okay, so how do we do this? Well, we're going to go to z-estimate difference of proportions. The z, because like I said, a difference of two normally distributed variables is normal. Estimate, because we're going to build a confidence interval. We want to construct a 90% confidence interval to target the difference between these two. And then it's going to be a difference of proportions. Okay, so if you want to do the GeoGebra along with me, go ahead and open up your GeoGebra. So let's come over here to GeoGebra. And you'll see that getting the answers is actually quite easy. Now, understanding what the answer is telling you and justifying the distribution, that's different. But anyway, we're going to hit the toggle. We go to the three dots. We go to probability calculator. And we go over to statistics. Okay, so you've been here dozens of times by now. We go to the drop down, and then we have to figure out what procedure we're using. Okay, at this point in the semester, we're in the 5th chapter, so we've covered lots of different inference procedures now. So you kind of have to, like as a process of elimination, go, work your way down to the relevant process. So which one are we doing? Well, we're doing a confidence interval. Remember, confidence intervals are estimates. So we're down here. We're not doing a test. We're not doing one of these. We're doing a test down, or we're doing an estimate down here. As we discussed, we're looking at proportions because these are both categorical variables. So it's not going to be any of these means. So now we're down to z-estimate of a proportion, which was chapter 3, and z-estimate difference of proportions. Well, we're looking at a difference between two populations. So it's a z-estimate difference of proportions. Okay, so then we put in the confidence level, and then which one is sample 2, which one is sample 1? Well, it's totally up to you. Okay, so what I like most people, I tend to prefer positive numbers to negative numbers. So I'll put the women in as the first sample and the men in as the second sample. But you can definitely swap that. There's no reason why you can't. The numbers will only differ in the sign. Okay, so the SIG and the sign. So there we go, and we're done. Basically, right? So there's our point estimate, right? We saw about a 9% difference among the sample proportions. But because of sampling error, we know that that point estimate's a little bit off. So what the margin of error does here, right, and this is the margin of error, this 0.0393, it gives us a nice idea of how far off we are from the actual parameter. Okay, so we take that margin of error, we add it and subtract it from both sides of the point estimate, and we get our confidence interval, right? So it's all there, it's all calculated for us. So note those numbers, and then we'll come back over here and let me kind of help you think about it a little bit more. Okay, so what do? We want 0.9, we put in 270, 750, we had 203 and 750. Yes? Okay, so don't have a lot of space here, so let me help you visualize what we're trying to do here. We're looking at the difference between the proportions between males and females, right? So it's got to be between -1 and 1, right? At the most extreme, you could have 100% of the females of normal weight and 0 males of normal weight. That would put you here at 1. Okay, but of course that's not going to happen, right? So that's the extreme case. The other extreme is all of the males could be of normal weight and none of the females for a -1. Okay, so those are the extremes. They obviously wouldn't happen. In the middle we have 0. What did we get for our point estimate? We got 0.09 or 0.089, right? So in other words, we got about, well, it'd be closer. I'm going to exaggerate a little bit here just so for our picture here. Okay, so we're trying to estimate this parameter of parameters. Okay, so it's a difference of two parameters. Where does that difference sit? Okay, so we have our point estimate here. Then we put a margin of error on the right and a margin of error on the left. Okay, and then so that creates an interval, right, a confidence interval that has some level of confidence that we're going to capture the actual difference between these two parameters. Okay, so that the point estimate's there in the middle. That's the 0.089. You don't need technology to tell you that. You just subtract the two point estimates. Then we add the margin of error on the right and subtract it on the left. Okay, so what were those numbers again? It was 0.0893 plus 0.0393. Okay, for a right endpoint of 0.1286. Okay, and then we take that same margin of error and subtract it from the point estimate. Okay, which gives us 0.050. So that's the margin of error. I'm sorry, that's the confidence interval. So let's write that down. So it's 0.050. It's 0.1286. So that's the interval. What does it mean? Okay, so now we have to interpret the interval. Well, the interpretation is very much like the classic, interpretation that we've seen with all of these other types of data, right? This is like the third or fourth type of confidence interval we've done, right? So we see that they all have very similar kind of interpretation, right? How does it go? Well, we start off by telling people what the confidence level is. So we are, or there is, 90% confident that the difference between the proportion of females of normal weight and the proportion of males of normal weight is captured by the interval from, and you can use a proportion or a percentage. I kind of prefer percentages at this point because I just think it's clearer for most people, from 5% to 12.86%. So maybe I'll just round it to maybe 12.9%. Hopefully that's not confusing. Okay. So we're 90% confident that the difference between the proportion of females of normal weight and the proportion of males of normal weight is captured by the interval from 5% to 12.9%. Okay, so on the exam, you write that, that's 100%. It's perfectly fine. But think back to chapter 4 when we were doing differences between, say, two means. When you have that structure of a population versus another population, then there's kind of like a richer number of interpretations that you can have, right? So this is a great interpretation. The other one is where you look at 0. Okay, is 0 in the interval? Is it not in the interval? Okay, so 0 is here. Notice that it's not in that interval. Okay, the lowest value in this interval is 0.05, which is positive, and the highest is 0.1286, which is also positive. So 0 is not in the interval. And so what that means is that 0 is not a plausible value for the difference between those two parameters. So, so we can say that basically a higher proportion of females are of normal weight than of males. Okay, so so we can say since 0 is not, now that doesn't look very good. Let's see here, since 0 is not in the interval, and all of the values of the interval are positive, females have a higher proportion of people of normal weight than males. There's a number of ways of saying this, but that's a perfectly good one. Perfectly good way of saying it. Just making sense? Whoops. I'm running out of room here. Let me pull this down right here. And then, not to confuse things, but just to make this as useful as possible, let me just add in another thing here. What's a maybe even more practical way of saying this? The proportion, the percent of females of normal weight is between 5% and 12.9% higher than the males. So our point estimate was about 9%, but it could be as low as 5% better or as high as about 13% better than the males. Okay, and so that's useful, right? If you're studying like public health and trying to understand if there's like gender effects with various things, in this case like obesity, right? It's very useful information. All right, so we did that kind of quickly without thinking too carefully about the requirements, the distribution requirements. So now let's go back and be a little bit more careful here. Okay, so, but before we do that, let me just see if you have any questions about what we've done so far. Does anybody want to ask about any of the steps here on this? We've done, let's see, in chapter 3, we had confidence intervals. In chapter 4, we had 2 different kinds of confidence intervals. And now, so this is our 4th time through confidence intervals. You know, if it kind of makes sense, just, you know, already for you, I think it's because we've practiced so much with confidence intervals. And so that's a good thing. So hopefully, you know, the idea here basically is making sense. Let's see. Where did those decimals come from? Which decimals, Lana? Which decimals? And you can talk in the microphone if you'd like to. It's you know, feel free to do that. The top with the margin of error. Let's see here. Oh, I see. Well, this decimal came from the point estimate. This decimal is the margin of error. So that came from GeoGebra. That's this margin of error right here, the 0.0393. Does that answer your question? So yeah, that 0.0393 came from GeoGebra. Okay, so let's go back through this a little bit more carefully. Let's talk about the distribution requirements. Let's look at the formulas that GeoGebra is using. We don't want GeoGebra to be a black box, right? That just kind of spits out numbers that we don't really necessarily understand where they came from. Let's try to use the formulas a little bit here. So yeah, here our key statistic, the point estimate, is going to be a p hat minus another p hat, right? So in our example, that was p hat, pf hat minus pm hat. Yep. So that's the point estimate. So this all works if pf hat or p1 hat minus p2 hat are normally distributed. So how does that happen? Well, there's 3 requirements. And these 3 requirements are going to sound pretty familiar to you. They're the same requirements we've seen over and over and over again. That may be a little bit different because of the structure of the data, but I don't think there's anything here that will surprise you. Okay, we are down here in this, let's see, where are we at? We're on this bottom left-hand box here. So this is inference for 2 categorical variables, which is what we're doing, right? In this example, it was gender and being of normal weight or not, right? So what are we doing? We're doing a 2-sample Z confidence interval for a difference of proportions. So there's 4 conditions that have to be met before we're justified in using the normal distribution. The first is that we have a random sample. Okay, so you'll want to bring this formula card with you, or at least parts of it, to exam 4 next week, right? And so you'll have to go through each of these 4 requirements. So first of all, do we have a random sample in this BMI study? Well, let's see. I'm going to move over to another page because I'm just running out of room here. So let me take this over to another page here for us so we don't have to keep writing over everything here. Just give me one moment. Okay, so going through those requirements on the formula card, right? So first of all, do we have randomness? We know that randomness is such a key principle for pretty much all of statistics, right? It helps us avoid bias, right? So does it say we have a random sample? Well, it says it's a survey. That's a synonym of sample. The other thing is that this is the Gallup organization, so it's like one of the top polling companies in the world. So very, very well respected scientific company that's using valid statistical techniques. So it doesn't say random, but I'm going to go ahead and assume random. Okay, so it's not done by some partisan polling company or something, right? So let's assume that first one a little bit. If you're on the exam and you're convinced it's not random, then just write down you don't think it's random and then continue on with the rest of the problem, okay? The second thing is independent observations. Okay, we have 2 different samples, right? So within each sample, we have to make sure that the females in that sample are unrelated to each other. We don't want 750 females from, one town in southern Utah or something, right? So we want it to be spread out. And the way we do that is by making sure that the sample is less than 5% of the population, okay? And so, whoops, I got a lot of things open here. So second thing, we take the sample size and we make sure that it's less than 5% of the population. So I don't know how many females there are, but if we solve this, we should get a good idea of what that minimum population size should be, right? So I'm going to divide both sides by 0.05. Okay, so let's see, we go 27. I'm sorry, I'm using the wrong one. It should be 750. My apologies. There's 750 females in the study, right? So 750 divided by 0.05. Okay, so 15,000. So yeah, there's definitely more than 15,000 females. Now, because the sample size for the males is exactly the same, I'm not going to do that twice because it's the same exact calculation. But there's certainly more than 15,000 males as well. So what that means is that the men in the sample don't know each other, right? They're not related to each other. They're just independent. Same for the females. Okay. The third thing we have to check on the formula card. Let's go back to the formula card. That looks kind of like a big mess, but we're familiar with this, right? It's basically saying we're going to get at least 10 successes and at least 10 failures in each of the samples. Okay. So 10 people in the category, 10 people not in the category, right? So in other words, and the rule of thumb is 10. That's basically checking to see if we have a large enough sample. You can't really do good statistics if you only have 10 people in your sample, right? So we'll have to check that too. And yep, so you'll have to pull out the calculator and do these on the next exam and on the final. Okay, so we go N1 P1 hat. So what does 1 mean? Well, that's the females, right? So we have 750, okay, and then we had 270 over 750 for P hat F, right? So we didn't actually have to do that calculation, right? Because we knew there were 270 in that category. So if there's 270 in the category, how many are not in the category? Well, that's N1 or NF P hat F, right? Maybe I'll go ahead and just pull out the F here so we're not confused by the 1 there, right? Okay, so, well, you can just subtract 270 from 750, right? Okay, or you can work through the formula. So we go 1 minus 270 over 750. No problem with that. So we go 750 times 1 minus, hopefully you remember this kind of inequality from chapter 3. We did the same thing in chapter 3, but we only had one population in that case, right? So if 270 are of normal weight, then 480 are not, right? Okay, so that's for the females, and we have to do the same thing for the males. So we go N M, number of males, P hat M, okay, so how many males are of normal weight? Well, 203, right? So that's, I don't even have to do that one. And then this one, it's going to be 750 minus 203 again, right? So let's speed that up and just do a subtraction rather than multiplication and division. So if there's 750 males and 203 of them are of normal weight, then 547 are not, right? Each of these numbers is more than 10. So we're good, right? That means we have a large enough sample. Okay, the last thing we have to check, and this is on the formula card, we have to make sure that the two samples are independent of each other. Okay, you don't want to have two overlapping samples. Okay, so yeah, if you've got a sample of males, you've got a sample of females, then they're basically not going to be overlapping, right? Or not very much, right? So we should have two independent samples of each other, right? So there's two kinds of independence. There's the within sample independence, and then there's the between sample independence. And we have both of those met here. So since those four conditions are met, then we can use the normal distribution. So the normal distribution will come with formulas. Now, formulas are here on your formula card. I recommend that you don't use these at all this semester, okay? We put them here for to give you a nice complete picture, but I don't use the formula by hand at all. I just go right to GeoGebra. So what does the formula say? Well, it says here's your point estimate. Okay, so that was the 0.089, right? Then you have the margin of error, right? So you go plus or minus your margin of error. So it's just like all the other confidence intervals we've worked with. What's the margin of error? How does it work? Well, it's a critical z-score because we're in the z-distribution. Okay, so much like in chapter 3. Then this part looks really weird at first, but if you take a deeper look, what is each of these expressions? Well, this is the standard error for p hat, right? So that would be the standard error for the first p hat. This would be the standard error for the second p hat. So you're basically like averaging the two standard errors together to get kind of an overall standard error for your sample, right? So you take that standard error, you multiply it by your critical z-score, and there you go. You've got your margin of error. You add and subtract that from your point estimate. Okay, so it's just like all the other confidence intervals we've done before. So there's a lot here that's similar to what we've done before. Now, like I said, you can do this by hand if you want, but I don't recommend it, at least not in this class. I recommend going right to GeoGebra. Okay, so on exam 4, just like we did on exam 3, if I ask you for the confidence interval between, for the difference of two proportions, you're going to have at least some partial GeoGebra output there, okay? I won't expect you to calculate this whole thing by hand, okay? All right, so we've made good progress here. We didn't finish chapter 5, but I think we're pretty much almost there. I mean, we did a confidence interval, and next time we'll do another confidence interval and then a couple of hypothesis tests, and then we'll be all done. So on Thursday, I'm confident we'll have at least 20 or 30 minutes to review together, then you guys have this recording that I've made. You've got this huge packet of sample problems. And then I think there's another review session that's going on. I probably posted about it. Let me see here. Did you guys get that? Let's see here. Yep, this one here. So I posted this about a week ago. This is one that the department is doing, or the STEM Center. Somebody at the college is doing this. Let's see here. Okay, so yeah, on this Thursday, they have one from 6 to 8. This one is at the Redwood campus, and it should be an SI 101B. Sometimes they do change these at the last minute, so if you get there and nobody's in that room, just go and talk to the person there at the desk for the STEM Center, and they'll send you in the right direction. Okay, so go to that if you can. I think it's useful. Anyway, come back on Thursday. We'll talk more. We'll finish chapter 5. Any last questions here as we break for the day? Okay, well, have a good one, guys, and see you on Thursday. Take care.